Hello everyone. This lecture is about fundamental aspect for the flow in a pipe, a capillary tube that we had also used for bundle of tube theory, and also between parallel plates, the Poiseuille flow. And it's a laminar single phase incompressible flow through cylindrical shape type of pipes or between parallel plates, where the flow is driven by the pressure gradient only, not that the surface is doing anything. Because if you consider flow between two parallel plates, the plate at the top can also be moved, so it can drive flow. That's not the case here. We have a tube, a pipe, or we have a parallel plate where they are both static and flow happens through them because of the pressure gradient, because of pressure driven fact. Why do we do that? Because we use the formula, if you remember, for flow in a cylindrical tube to obtain the permeability for one tube that was r squared over 8, right? Now I want to go to the fundamental aspect of it, why it is that the velocity inside that tube has the minus r squared or minus r squared divided by 4 mu dp dz, if you remember from the second lecture we had before. So this is all about it. For doing that, to understand how the fluid dynamics of the flow inside channels is driven, we need to go back to the fundamental equations of mass and momentum balance in tubes, in channels. Mass and momentum balance for incompressible laminar flows can be written by continuity equation and the laminar and kind of a well-posed Navier-Stokes equation that is momentum balance for a particular fluid. Momentum balance in fluid dynamics, F is equal ma, is written as Navier-Stokes equations, that is m times the acceleration is the forces acting on the fluid particle, on the fluid stream, for example. So when we want to do that, let's consider the flow inside a tube, and if you remember, the tube was in, for example, the coordinates, one is radial coordinate, the other one is z coordinate, and if you recall, the profile of the velocity was derived in the second lecture when we wanted to do permeability with bundle of tube theory, and we had some conditions that it was a laminar flow, it was fully developed, boundary layer developed, boundary layer, and it is at a steady state, and also importantly, no slip at walls. So under these assumptions, we actually managed to write what's the velocity profile, which is only a function of r. It does not change across z. That's the fully developed state means, that it does not change across cross-section, so entrance is actually avoided. Laminar flow, so Reynolds is a small, and we have a steady state condition, so no ddt, and the no slip condition means velocity at the wall contacts is 0. So let's write first mass balance or continuity equation, and then the momentum balance, which is Navier-Stokes. Now, I have not yet made any lecture about Navier-Stokes in detail, but for now you need to accept from me what are the F is equal ma for the stream of flow like that in fluid mechanics. I'm going to explain to you what they are. So the continuity equation is written up here in radial or cylindrical coordinate, in which the velocity in general will have a dimension across z axis. So this is the velocity, this is my z axis, so that is z. Then this axis is r, and there is a theta, right? There is a rotation theta as well. That is the rotation direction. Velocity that I have here is only in z direction. So my velocity, a vector of velocity, which will be velocity in r, theta, and in z, It's only Vz that is non-zero. Both others are zero. So my velocity is only velocity z. That's important for me to know. So therefore, when I look into that and I see that it's a fully developed flow, which means that Vz is not a function of z direction. It does not change along the z. When you look at the continuity equation, ddr of Vr is here, but Vr is zero. V theta, which is the rotational one, is also zero. I only have parallel to the cylinder, to the pipe, actually, velocity component, and that is the derivative of it over z is zero naturally because it's a fully developed flow, fully developed boundary layer flow. So the continuity equation with these system setting is already trivially satisfied. Now, how about the momentum balance? How about the Navier-Stokes in the parallel to the direction of the cylinder, the pipe? So you see the z direction momentum balance here. The equation has this part, which is density times acceleration. Density is mass per volume. We are in Eulerian system, so we are writing on the volume, on the fixed volume, so mass per volume of the system, and that's the acceleration of my fluid, the stream particle, and then it is equal to the forces acting on the system. The first one here is the gradient of the pressure across z-axis, and the other are the forces that are acting on the stream of the flow because of the shear, And that shear is the force that is because of viscosity is taking place. So it is mu divergence tau, divergence of shear in the system, which actually is the equation that you see down in here. I plotted it for you this way so that I don't spend time to write it down for you. Now, if you look into the left-hand side equation, I have density. And if I look closely, because what I see is very small, is that all of the terms in the left-hand side are all zero. There is ddt of Vz, if I use my own memory. Then I have Vr ddr of Vz, which is also zero because Vz does not change in R. Then I have the theta part, which is dVz d theta, which is again zero. And I have the dVz over the z direction, but again I know that velocity z does not change across the length of my pipe. It is actually fully developed velocity. It's only Vz is a function of R. Vz is only a function of R, not anything else. So the left-hand side becomes zero, and I get the right-hand side. The right-hand side, the first term, is a function of R, so 1 over R ddr, R dVz over dr, dVz over dr is non-zero. That's the shear that actually acts here in front of the fluid movement, which is exactly what I need for the balance of the pressure drop. The rest of the terms are again trivially zero because they get V R, there is also V theta, etc., that are actually zero trivially here. So using the balance equation and continuity equation, which was satisfied with my assumptions, with my setting, and the z momentum, left-hand side zero, so I write zero is equal dp dz, so I write it the pressure drop over z-axis, and if you write the momentum balance for r and theta, you see that all the terms are trivially zero except dp dx, or I'm sorry, dp d theta and dp dr, and they become zero, so therefore pressure drop is not partial P over Z, it's derivative P, because pressure is not dependent on any other coordinates. It's only dependent on Z axis. That's why I can avoid writing it as partial P over partial Z. I write it dP dZ, right? Because pressure only changes across the Z axis. And then plus viscosity, then I need to be careful here. I hope I remember well. Otherwise, I need to re-record myself. I guess I get it here. So it's over d1 over r ddr of my r dvz over dr. The rest of the terms are zero. Fantastic. So I get the formula, that allows me now put dp dz to the other side. And so instead of writing minus dp dz plus blah blah blah, I can simply write that equals 0, go home, and I am here and making it equal. Fantastic. dp dz is only a function. Actually it's not a function of z. Actually dp dz is actually constant. It's the pressure drop which is linear in this system, right? Now I know vz is only a function of r, so this here is only a function of r, while this part here is not a function of r. So it's constant. It is constant. So let me just make a clean board now for you. This is constant over r, but this is a function of r. So that practically means this factor is constant, this derivative. Now let me do the math here. Put r on the top, bring viscosity here. So I write an equation for ddr of r dvz over r is viscosity over r. Viscosity, I'm sorry, not over r. R comes to the denominator. So it's great that I'm doing this way. So you see that how it is derived. So viscosity comes in the denominator, r goes there. So it's r over viscosity dp dz. Fantastic. Now, I know that I can integrate it one time. If I integrate it, I get r dvz over dr equals, this is a constant function of dp dz, and there is 1 over viscosity here, and then r integration becomes half of r squared, and there will be a constant c for the integration. Now I know that my velocity at r equals the capital R, which is at the wall, it is 0. So when I put capital R here, I want dvz, vz to be 0. That's one boundary condition. So this is boundary condition. There is one other boundary condition that is very intuitive because of symmetricity of the problem I have. Look at the center line. Vz, the derivative of it over r should be 0. Derivative of Vz at center line with respect to r should be 0 because of symmetricity that I have. And that means that this boundary condition is very helpful, because when I put r 0, it means that this boundary condition helps me get rid of c. So c is 0. Then I get to know that eventually, maybe I better just write it up in here, r dv dz, r derivative of my velocity over r becomes 1 over viscosity dp dz, and then half of r squared. C became 0. Now let's cancel r. The power 2 drops out. Then I get the dv over r becomes 1 over 2 viscosity dp dz. And now, again I can, and there is one r here, sorry. Now I want to integrate it again. This is again constant in r. There is a linear functionality of r. So velocity in z direction as a function of r is 1 over 2 mu dp dz. And here I have r squared over 2. Now this 2 with that 2 becomes 4. See, I am getting the formula that we already had. So Vz become, and sorry, there will be a c prime, a constant of integration coming too. So 2 will be 4. So I get 1 4 mu dp dz r squared plus c prime. And now I am going to use my first boundary condition, which says velocity at r equal the radius of your tube is no slip condition, and it must be 0. If I put r squared here, my Vz will be 1 over 4 mu dp dz r square plus c prime. So therefore, c prime, this must be 0. C prime will be minus 1 over 4 mu dp dz r square. And so I can plug this c prime here to eventually get my vz, to eventually get my velocity in z direction as a function of r to be 1 over 4 mu dp dz remains, so dp dz remains, and then I have r square and minus r square. So what I do is I want r square, the capital R, to be, because it's bigger than a small r in general, so I write it as r square minus r2 square, and so I put the negative sign here, and then I delete this 1 here, so that would be my equation. So if I write it cleaner for you, that will be minus 1 over this r square minus r square dp dz. See, this is the formula that we found for Vz as a function of r, and remember that we did Q over cross-section area was average velocity because of Darcy's law, and so we did the integration of minus 1 over 4 mu r square minus r square dp dz from r0 to r is capital R divided by the total cross-section, which is pi r2. And that was when we did the calculation of the integral in the lecture 2 to ultimately find out that the average velocity across this pipe, across this cylinder, across this tube is minus what, if you remember? R square over 8 mu dp dz, which then made us say that this r square over 8 is permeability of one tube. The tube, depending on the pressure drop that it has and viscosity of the fluid there, the permeability of one tube will be r square over 8. And that's why we used r square over 8 as the permeability of that tube. That has direct implication for laminar flow, fully developed because velocity should not change by z. It is a steady state, so ddt were all gone and no slip at the walls. Now, this was what I presented for tube flow. We can repeat the very same thing for parallel plates flow. So flow that is between parallel plates. So if I delete these, you will find that the very same mathematical formulations hold for parallel flow between the plates. And that's actually what matters for us in geosciences as the flow between plates of fractures. So there we need to do a different perspective compared to what we just presented here. Where we want to do now in flow between parallel plates compared to the flow in a pipe is that I have a parallel plate and then I have a profile like this. For this one, now I need to again find the velocity distribution, but here was in radial coordinate or cylindrical coordinate, while for the parallel flow between plates, my coordinates are Cartesian. So it is x, y, and z. So I would like to find out what would be the profile of the velocity for this laminar steady state flow, laminar fully developed, steady state flow, and no slip. Now I would like to understand how could I write it for flow between two parallel plates that are, let's say, with an aperture like H or A apart from each other. The very same formula, the very same boundary conditions here hold. But this was for tubes, circular tubes, that ultimately allowed us find the velocity distribution. Now I would like to do mass balance, continuity, and momentum balance now for flow in X, Y, Z is not relevant here, it's a 2D flow, so Z direction instead of R, theta, and Z, which is cylindrical coordinate. For cylindrical coordinate, I would like you allow me delete these and write for you the final formulation that we found so that you keep track of what we are going to do for the other one, and therefore you see that the board is now clean, and I can write that what we found was Vz as a function of R was minus 1 over 4 mu R square minus R square dp dz, or d cap d just derivative, not partial, because p is only a function of z. That's the Poiseuille flow for tube. Now here I do again momentum balance, and if I write the momentum balance and mass balance, I see the equations here. So let me delete this so that you are not being interfered with the two equations at the same time. That's the mass balance continuity equation for Cartesian grids, for X, Y, and Z. And the bottom one is the X momentum balance, because now I am going to write my equation for X, Y, Z, because it's flow in between parallel plates. So the very same analogy as in the tube here holds, because here I would say, since the system is fully developed, velocity is only across the x-axis, and it does not change in the x-coordinate. It does not change. It's only a function of y. So velocity is not a function of x nor the z one. For the momentum balance, since I have density times time derivative is 0 because it's a steady state, then I have velocity ux ddx of velocity in x direction. Ux is not a function of x, so that becomes 0. Ux is, then you have uy times ux ddy of that ux, and that you have derivative of ux over y, but uy is 0. So then you see that uy and uz are 0, and therefore you end up with a formula that is pretty much similar to the radial coordinate or cylindrical coordinate. Now here you get the formula that says 0 is minus dp dx, because pressure is only drops across the x-axis. Then you have plus viscosity, and then you have the Laplacian u, which is the second derivative of ux over y coordinate. That's very interesting, because now instead of this radial component, this is radial system, now you get based on x and y axis. What is your objective? Integrated to find ux as a function of y. Here we integrated it to find velocity z as a function of r, radius coordinate, and we found it was minus r2 over 4 mu dp dz. Now here I would like to find what would be the formulation for my velocity here. What I do, I put dp dx in the other side, so I get dp dx equals mu, second derivative of u over y axis, And then you see that this is ux is a function of y. So this is a function of y, but this is not a function of y. This is a function of y, but this is not a function of y. So this is constant. So viscosity goes in here, and then you can make one integration for the du x over y2, which is 1 over mu dp dx. If you do one integration, ux derivative will be found, which is 1 over mu dp dx y plus the first constant, and that's your first constant, which then you use the coordinate, for example, in the center of your gap. So your gap goes from minus a to a, for example. That makes it much simpler to apply the very same symmetric law, that derivative of ux over y at the center. So if you take center to be your y0, depending on if you want to have y0 to be the center of your channel or at the bottom of it. I suggest you put it at the center, which is very similar to the other case. So at y0, which is the center, then we know that derivative should be also 0, which means that if y is at the center, c is also 0. And then you can do one more derivative to get ux as a function of y to be 1 over mu dp dx. Now here I have y square half, now plus the next constant. How do I get the next constant? I know that ux at y equals, let's say, minus h half, because its total gap is h, so this is half of h negative. At minus or positive h half, it doesn't matter. It is at minus h half or plus h half, doesn't really matter. Plus or minus, that should be 0 because no slip condition. No slip. So I put h half here. I find that ux, which must be 0, is 1 over viscosity dp dx, and y to the power 2, you see minus or plus doesn't matter. It becomes h squared over 4. So h half to the power 2 will be h to 2 will be 4. Divided by 2, it will be 8. Plus c prime will be 0. Therefore, c prime will be minus 1 over mu dp dx h squared over 8. And now I get back to this formula and write my ux to be 1 over mu dp dx. And then I have y squared over 2 plus c prime, which is minus 1 over viscosity taken, dp dx taken, h squared over 8 not taken. So I put it this way. Now if I put the common denominator, I can do that, but there is one thing that I need to just make sure, that the gap that I have is h, and my y-axis is here, and the channel goes to minus h half to plus h half. And that's exactly what we did. And so you can do this way, or you can bring minus here, put minus here, and plus here, and that would be your ux. Now, if you do this and find average velocity, like what we did for the tube flow, to say it's q divided by area, and so integrate your u here, you integrate your u from 0, from minus h half to h half, that would be your u times dy, so ux dy will be your element, divided by cross-section area, which would be, in this case, h. The other size is 1, so we don't consider that. You will get to know that the permeability of parallel flow between two plates of gate 8 will be h squared over 12. That will be the permeability of the parallel flow. Here, when we did the Q Q for us, which was over A, that was average velocity for us, right? That was average velocity. So this is average velocity. That was from 0, R, from 0 to capital R, U, Z times 2 pi R dr. And then it was divided by pi R2. So if in the earlier record I have missed this term, please remember there is this term there as well, but you naturally know that. So this is the average here, and that led to the K of the tube to be R squared over 8. But here, the K of a fracture, parallel plate, will be H squared divided by 12. So that's actually what many times in the scientific papers, etc., you see that the fracture permeability many times is taken as H2 divided by 12 because of Navier-Stokes under laminar, fully developed steady state and no slip condition at the wall. Average velocity for radial coordinate becomes that permeability of the tube, wormhole or something that is cylindrical, is R squared over 8. Navier-Stokes for laminar, fully developed, steady state, no slip at the wall, tells you that the permeability for the flow between parallel plates is H squared divided by 12. Now I hope that the concept behind using R squared over 8 or H squared over 12 is clear to you all. Once more, if earlier in this board I did the calculation of the U average for Q over cross-section area A, where is my mind? So I do UZ, 2 pi R dr is the area fraction for a disk which has dr thickness, and that's the area here, and it's in the distance r. 2 pi r is the perimeter, thickness is dr. And then with this integration I get the R squared over 8. Why? Here integration is very simple because it's parallel plate, and I just need simply to take a distance like that with the dy axis. That's all. Thank you very much for this. Please watch. In the case you find that I miss a negative sign or do this and that, put it in the comment. Nobody's perfect. I write them all from my head, and I do my best to write it well, but there are some tiny notes that I may miss, but I rather to go one sweep of all so you see the entire story, so the memory chunk in your brain is made for the entire concept of Poiseuille Flow. Thank you very much. Have a nice day.